Be explaining Julian Paik's concepts 1 through 4 questions. So these are going to be covering the buoyancy and hydrostatics. First question, we can see just from the general setup that this is a manometer with an unknown fluid and an unknown density. The constant pressures right here, there's two different heights. One is from a low density gas, has a height of 8 centimeters. The second of the known fluid has a height of 71 centimeters. Within this manometer, there is a metal ball, which is being held up by buoyant force. Of which is also attached to a scale, and we can calculate the new mass of the ball after being applied a buoyant force. So first, let's go ahead and find the buoyant force acting on the ball from the unknown fluid. The ball initially has 526 grams, but when it's within the fluid, the mass measured from the scale is 131 grams. And so that difference in mass is what's going to be taken into account in calculating the buoyant force. So we're going to multiply that in kilograms times 9.81 as the gravity constant to get 3.87 newtons as the buoyant force acting on this ball. The second thing we're trying to find, part B, is the density of the unknown manometer fluid. So we know that the buoyant force is equal to the density of the unknown fluid times gravity times the displaced fluid. We know that this ball has a quarter of its volume exposed to the atmosphere, meaning that 3/4 of the ball is displaced within the fluid. So in order to calculate this displaced volume, what we're going to do is 1 minus 1/4 of the exposed ball times 4/3 pi d cubed over 8, which is the volume of the ball. Multiply that by this equation up here that we see, and we're going to solve for the density of the unknown fluid to find that it is 8,037 kilograms per meters cubed, which is about 8 times more dense than water. Third thing we're trying to find is the absolute pressure at point A within this little bulb. Since this is a low density gas, we can assume that its hydrostatic pressure is very minimal compared to this. And what we're going to do is we're going to add this hydrostatic pressure of the unknown fluid acting on this point A. And so to sum up the pressures, what we're going to do is from the hydrostatic equation, pressure at A is equal to atmospheric pressure plus rho gh, that is rho of the unknown fluid, and this is height too of the unknown fluid. And in doing so, we find a pressure of 1.55 atms. So now going on to question 2, we have a water gun that's attached to a tank of water above it. From hydrostatics, we're going to get a fluid flow through a U-bend and then out of this nozzle right here. What we're trying to calculate is, from a momentum balance, what is the force applied to hold this water gun stable and in place. This is a great problem, and I would love to explain this for you guys. So this is Bernoulli's and macroscopic momentum balance. So first things first, we need to calculate V4, which is the velocity out of the nozzle, and V3, which is the velocity in the pipe, essentially. To do that, we're going to do volumetric flow rate over the concentric nozzle, and then volumetric flow rate over the area concentric of the pipe to get 5.09 meters per second of volume or velocity out of the pipe and 318 meters per second in the pipe. Next, we're going to do Bernoulli's from points 3 to points 4, so that's across the nozzle. Assuming that is horizontal, so no change in height, and using the velocities we just solved for, we can find that P3, which is within the pipe, is equal to 12.9 kPa. Now we're going to do Bernoulli's from points 1 to 2, which is the top of the tank up here, to the bottom of the tank, to find the difference in pressure. We know that the top of the tank is exposed to atmosphere, and its velocity is negligible compared to the velocity in the pipe. V2 is equal to V3, as there's no friction losses. So we're going to calculate for P2 from our extended Bernoulli's, with now a difference in height, which accounts for the U-bend right here of 0.115 meters, to find that P2 is equal to 12.4 kPa. Plugging this back into a momentum balance now, we're going to find the convective forces plus the pressure force minus this applied force, which is what you have to apply in order to hold the nozzle steady, is equal to 0. So to find this mass flow rate, we multiply density times volumetric flow rate in order to get 0.001 kilograms per second, moving the convective forces over and leaving the force applied on the left side, as well as moving the pressure force over. We can solve for the applied force of what you have to hold in order for the nozzle to remain steady, and that's 3.89 newtons.